Okay, so let us take one numerical example. We will be calculating a link budget for a given system, a millimeter wave system. We are considering a simplified transmitter and receiver circuit, where the transmitter is shown here. We have a millimeter wave source followed by one antenna, and in between we have antenna feed network. Antenna feed network is lossy, it can attenuate more than 50% power. Next, at the receiver side, we have the receive antenna, then antenna feed network followed by band pass filter. We typically use a band pass filter just after the antenna to minimize the thermal noise contribution, as well as to minimize any undesired interference from other sources. And immediately after that, we use a low noise amplifier, for which noise figure is very small. We will discuss later that why we need to use a LNA as soon as possible just after antenna, because in any chain of a given receiver, the first component determines the overall noise figure of this receiver. So, if I use a smaller value of noise figure for the first component, then overall noise figure of the receiver it will decrease. Next is channel selection filter. It can be a switch also, followed by high gain amplifier and then the demodulator. So, some typical values are given for a 60 gigahertz system. Transmit power to antenna is 15 dBm. Loss in transmit antenna feed network is 5 dB, it is quite high. You see 3 dB represents 50% loss, even it is more than that. Transmit antenna gain 12 dBi, free space loss at 5 meter, considering n equal to 281.98 dB, and reflection loss due to multipath. So, due to multipath, we are subtracting some power which is given by 15 dB. So, input signal level at the receive antenna in dBm we can calculate. So, the positive contribution is due to transmitted power and the gain of transmit antenna. So, 15 minus 5 plus 12 minus path loss minus reflection loss, it comes minus approximately minus 75 dBm. So, this is the power signal level at receive antenna. Now, at the receive side, let us say these are some typical values given here. Feed network loss 5 dB. So, that means gain is minus 5 dB we can say, or cumulative gain just after antenna due to feed network minus 5, and for any passive components which for which gain is less than 1 or lossy network, noise figure, again noise figure is the ratio of SNR at the input to SNR at the output. It is equal to simply gain of the device. So, if any device provide 5 dB insertion loss, its noise figure will be 5 dB. It is followed by a BPF, for which loss is 1 dB, cumulative gain minus 6 dB. Next, we have a LNA, then LNA gain is given 20 dB and cumulative gain then 5 plus 6 minus 20, it comes 14 dB. Channel selection switch, it has a loss of 5 dB, and then it is followed by one amplifier and cumulative gain is 39 dB. But when we are considering total gain of this chain, we did not calculate the total noise contribution due to this chain, and also what happens for the noise what is coming with the signal. Some noise again will be collected by the receive antenna due to the radiation, blackbody radiation. So, we did not consider all those effects So, because we do not know till now how to calculate that. So, after this we will concentrate on that topic, how to calculate the overall noise contribution and hence overall SNR of the receiver. So, let us start the next topic. There are many different sources of noise: thermal noise, flicker noise, short noise, 1 by f noise, but here mainly we are going to consider the effect of thermal noise. So, it happens because of the random vibration of molecule, this is due to thermal agitation, and as the temperature increases, then their thermal agitation increases and noise contribution also increases. And we can model a thermal noise by a by all the frequency component by a random variable which has all the frequency component. So, that is why sometimes we call it a white noise which has all the frequency components. Now, since our receiver, it will have a finite bandwidth, it can't pick up all the thermal noise components, it will pick up the components whatever we have inside bandwidth. So, for now we will consider ideal bandpass type response. So, that means the bandwidth whatever a receiver has, it will be we will represent it by a rectangular window function, and below that below or above that frequency range, the contribution of thermal noise is simply 0, but actual noise bandwidth is different, that we will discuss later. So, then from a resistor, if we have a resistance R which is let us say at temperature T, then noise power generated by the resistor we can write down, that is equal to Kt into Br, where B is that bandwidth of that rectangular window function. So, in general then let us represent one resistor R, then the noise power, this is given by K T, where T is the temperature of the resistor, into B into R. Then if we represent this noise by a noiseless ideal resistor in series with a noise source, let us say the voltage RMS value, it is E n. In that case, E n, this is equal to it is 4 kTbr it can be shown that the noise contribution, it depends only on the temperature of the resistor, not the resistance value. Okay, let us consider one scenario. If we have any components, it can be a passive component, it can be an active component. Now, we are using it in this system. Let us say one source is connected to this component, source resistance is given by R and it is matched to a load that is also given by R. We are considering a matched scenario. So, this input side is matched to resistance R and output side of this 2-port component, that is also matched to R, and the source resistor, it is at a temperature Ts. So, now whatever noise generated by the resistor at the left hand side, it will be the input to this 2-port device, and depending on gain or loss, it will be attenuated or it will be amplified, that noise contribution from left hand side, and it will be delivered to right hand side. So, in addition to that, this 2-port component itself, it will produce some noise. So, total noise contribution at the output side N naught, this is equal to, let us say, gain gain of this 2-port network is given as G, then N naught, this is equal to N internal, which is being added by this device itself, plus gain of the device multiplied by whatever noise being delivered by this device at the left hand side. Let us say that is given by N incident. So, G into N I. Now, from this N naught, how much power can be delivered to R, a given resistor? So, let us model this whole source by an equivalent resistor R and an equivalent noise source, which is given by E n. It is connected to a load, matched load R. From maximum power transfer theorem, we know that maximum power from a source that can be delivered to a load only when this load resistance is equal to source resistance. So, in that case, if we calculate what is the maximum noise power delivered to the load, it is given by, let us say, noise voltage is E n, then the current component is E n by twice R. So, I square multiplied by R, this is equal to E n. If I put the value, this is K 4 K T B R multiplied by 4 R square into. So, it comes K T B. So, you see one interesting thing, that the maximum power, that maximum noise power that can be, which can be delivered to a matched load, it is K T B. So, it depends on Boltzmann constant K, temperature of the device, this is the noise temperature of the device, and bandwidth. It does not depend on any resistor value. So, this is one important observation. Now, let us go back. Let us say we have a resonator, a tank circuit made of L and C. Then noise power stored in one particular component, inductor or capacitor, it can be shown that it is half of the total available noise power. So, total available noise power, if I consider per unit hertz, it is K T per hertz. The noise power stored in inductor, it will be K T by 2. Similarly, it is K T by 2 inside the capacitor. We can also prove it here. Let us consider this circuit. It is connected to this noise source, and which is represented by an ideal noiseless resistor R and the noise source E n. Then now we calculate E c, average energy, stored energy in the capacitor. This is half C v square. So, we can calculate this half C v square as C by 2 integration 0 to infinity, then the transfer function square, H f is the transfer function of that circuit, into N f d f. So, N f, this is the noise power spectral density due to En, because En it's a function of frequency and we are considering Nf as the one sided power spectral density of this En, and Hf, since L and C is given, we can calculate what is the transfer function. Hf equal to simply 1 by 1 plus j omega r c plus r by j omega L. This is the system transfer function. Then take magnitude square and put it in the equation. Then we calculate. Now we are considering the normalized value kT per unit hertz, but we have a finite bandwidth here. So what we can do, we can arbitrarily narrow down this transfer function around a midband frequency, let us say f naught. So integration limit will choose from f0 minus to f0 plus, and we will consider the frequency bandwidth is very narrow, so that this Hf more or less is constant. So in that case, you put the values here Hf, and Nf is represented by a constant value at f naught, Nf naught, and it comes out. And if we put the values here and solve it, then it can be shown it is equal to N f naught by 8 r. So put the value of N f naught, it comes kT by 2. So kT by 2 noise power is stored in capacitor. Similarly, another half is stored in inductor. Nf, this is 4 kTr. So whenever we use the expression noise power that is equal to 4 kTr, it is actually a simplified form. We have a more accurate form which is given here. Nf, noise power, thermal noise power, you remember, that is equal to 4 kTr Hf by kT. Actually it is divided by this exponential function, it is shown here by to the power minus 1. So exponential Hf by kT minus 1, this is the general form for thermal noise. And under a special condition, when Hf by kT is much less than 1, it is called Rayleigh-Jeans approximation. And you see, if I put Hf by kT is much less than 1, that means we are considering low frequency high temperature case. So for lower millimeter wave frequencies, we do not have any problem, we can use this approximation. But if we go to higher frequency, let us say near to 300 gigahertz, and go for space application where the temperature is negative, in that case we can't use this approximation, we have to use this whole form. But for indoor channel modeling or whatever we are doing on earth surface, where we use room temperature 290 Kelvin, in most of the cases this formulation is valid below 100 gigahertz, and we can write down then Nf, this is equal to 4 kTr watt per hertz. Then the corresponding noise voltage RMS value. So already we discussed previously, we used another parameter En. So that is square root of 4 kTr volt per hertz. Then power delivered to a match load, already we have seen this is equal to kT, it does not depend on R, this is watt per hertz. So available noise power is independent of any resistor. Now let us say we have a receive antenna. So antenna, it will generate some noise. So whatever noise coming to antenna, it will be attenuated by the antenna loss. In addition to that, antenna will add some extra thermal noise. So we can represent an antenna by an equivalent noise resistance, which can be given by R, and let us say the noise equivalent noise temperature is given by Te over a bandwidth B hertz. Then we define the equivalent noise temperature of the antenna as T E equal to N A by K B. So, this is the definition of any equivalent noise temperature. So, not just for antenna, we can also define this equivalent noise temperature of any amplifier also. So, let us say the previous example, or let me draw it again. We have one amplifier which is a 2-port network. At the input side, I am representing the source resistance by R, which is at a temperature T s. Now, amplification factor is given by G, then the effective noise temperature is given as T E. We have a matched load here, then noise power coming out from the amplifier is N naught. Now, if I consider left hand side, we do not have any noise source, then whatever noise power absorbed in this matched load, it is due to the internal noise power generated inside this amplifier. So, in that case, that means we are considering T s equal to 0, and we do not have any noise contribution from left hand side. So, whatever noise we are having at the output side, it is due to antenna only, due to the amplifier only. Now, we are representing this amplifier by one noiseless amplifier G, and the noise produced by the amplifier we are representing by a resistor, equivalent resistor. So, in the antenna example, we designated it by R and. Here, since we are considering matched scenario, let us consider this as R. So, in between these two R, we have a noiseless amplifier, and whatever noise actually coming from this practical amplifier, we are representing by a noise source on left hand side. Then the effective noise temperature, it is given, let us say, by T E. Then noise power, this is equal to K T. So, noise power generated by the left hand side noisy source is K T E. It is passing through the amplifier. So, it will be multiplied by G, and then if we consider a bandwidth of B, we have to further multiply it by B, and that is equal to the output noise N naught. So, effective noise temperature of this amplifier T E, we can write down this is equal to noise power at the output divided by this is K B into G, and if I consider per unit hertz, we have to just put B equal to 1. So, this represents the effective noise temperature of this amplifier. Similarly, we can do it for any lossy device also in general. Now, we already have seen what is the effect of noise for any 2-port network or for any antenna. Now, receive antenna, it can collect also radiation, blackbody radiation. So, what is blackbody radiation? Let me first discuss it. So, let us consider earth surface or any object. It can be human body, it can be any home furniture, any building, anything. Now, from Planck's law, we know that it will continuously radiate, and that radiation, it is a function of temperature and frequency. So, if I plot radiation intensity coming from any black body, it varies with frequency f, and we are plotting the radiation intensity, or sometimes we call simply radiance L. So, this peak value, it depends on the temperature of that object. For example, sun, its temperature is approximately 6500 Kelvin, and for which this peak value is at optical frequency yellow line. Now, if I consider ground, earth surface, and temperature let us say 300 Kelvin, then in that case this peak value, it corresponds to infrared frequency range, IR range. And if we go further down, sorry, this is not versus frequency, this is versus wavelength. So, if we go further down, that means if we decrease the frequency further, so we have this spectral component, it decreases, but it is not negligibly small at millimeter wave frequencies. Now, if we have any antenna, let us say it is focusing towards earth from satellite, then it will collect this radiation which is coming out from earth's surface, and we have a degrading effect on the antenna performance. Similarly, any earth station antenna, it can point towards sky and it can pick up the radiation due to sun, it can pick up radiation due to atmosphere. Atmosphere also has secondary radiation, dwelling radiation, and also it can pick up radiation from other galactic sources, and all these are sources of noise. This noise is superimposed with the signal power, and it will degrade the SNR of the antenna and receiver system as a whole. So, next day we will see that the brightness or this black body radiation, how it affects any SNR or the receiver performance, and then we will combine the noise figure contribution of all other components in the receiver chain, and combining this all the effect due to the black body radiation and noise contribution of the receiver chain as a whole, we will calculate the SNR of the receiver. Okay. So, let us finish here. Thank you.